these things. Okay, this is an overview. I'm not going to go into any problems in details, but I will comment on some of them as we go along. So that's just the title. This is a problem that I'm looking at, and it's only in 2 dimensions. Okay, 3-dimensional wave current interactions are different. So this one's only going to be in 2 dimensions, and that schematic says what you're dealing with. And of course, immediately, if you look hard at it, you can see that there's a problem. And the problem is that when you look at the definition of the current is only defined below the wave trough, because the current is defined to be a time average, and you can only do this if it's below the wave trough. So this is a huge problem. It's very difficult in practice to measure these things, but where you need the information most, which is near the free surface, that's where you have least information. So even the structure view is very difficult. And if you're measuring for comparisons, this is all that you can measure. You can measure some things above the trough with regard to the wave properties, but you cannot measure the current otherwise. So when if you're thinking of using a stream function method and you want the current to be known on a stream function in a fixed frame of reference, it's a very difficult problem. So we'll assume that we can solve these things without worrying too much about them. I'm going to say something about the type of models that are described here. In practice, these are not sufficient. But as Robin Johnson pointed out in the previous talk, classical applied mathematics has a huge amount to offer in these fields. And provided you understand the limitations of your model, you should not be afraid to use it. And I'll show some practical applications in a little while. Okay, so I'm assuming that the usual type of things hold, that you have an amplitude, you have a mean water depth, and you have a frequency. It's single frequency waves. If it's a linear spectrum, you can add all the bits up. I'm not going to worry about viscosity. I'm not going to worry about turbulence. But I'll say a little bit about some of the effects of these things in a moment. Okay, so there are 3 classes of profiles that you need to consider. And the 3 classes of profiles are where you have a constant current, and when you have a constant current, you have an irrotational wave field. So the potential or whatever satisfies the Laplace equation and you're on your way. So we know quite a lot about this. We don't know everything, but we know quite a lot about this. The second one is where you have a linear profile. A linear profile, just a straight line, does occur in some cases. So I'm not looking at a combination where you take a bilinear profile or a multilinear profile, which has occurred in the previous talk, just one of them. Now insert the word reasonably. Okay, reasonably well understood. You don't know for certain. There are things in this that you don't really understand. And then the last form is the one that I'm interested in, and that's where u is an arbitrary function of z. Okay? Now the question is, of course, at this stage, do you always need to know about an arbitrary function of z, or can you use one of the other 2 instead, which are much easier? So there is a question there that you need to know. And this is something that we all think we understand. And that's that if you have irrotational flow, you can get a velocity potential. Okay? And we'll say a little bit about the structure of that velocity potential in a little while. Okay, some requirements. The reason that I'm looking at this problem is a very simple one. You have 2 types of solutions. You have local solutions, which is the here and now, and you have global solutions. So in other words, if we know the solution here, do we know the mean flow properties at some distance ahead? So that's the first thing. And the second thing is, when you have those, can you then get a new good local solution? So the 2 problems are absolutely intertwined. So to think of it in a simple context, you have a wave field here, and this does not have to be in water waves, it can be in any wave system. You have a wave field here. You change the characteristics very slightly. So for instance, the water depth might change a little bit. Or if you're in some inhomogeneous media, the density might change a little bit. Can you then get the gross mean properties, the amplitude, the wavelength, and frequency at some other point and then construct a new local solution? Can you do that? And the answer is, that is as important as finding a local solution. You have to be able to do this. And if you want a nice simple example, think of waves crossing a jet-like current, which was talked about previously. As you go across the current strength changes. As that current strength changes, the amplitude changes, the wavelength will change. Let's assume the water depth is the same. So at each of those points, can you then get a local solution, an accurate one, based upon your global structure for that particular set of changes? So it's very important. It's very important. And the approximation that's usually made is to assume that you have a slowly varying approximation. Formally, what you assume is that the changes in the wave properties, like the amplitude and the wavelength and perhaps the water depth, occur over many wavelengths. Is this right? We don't know. We don't know. We just assume that it's going to be okay. But what we do assume is that locally the amplitude is fixed and locally the wavelength is fixed. A key property in all of this is that there are no reflected waves. That's a key property in all of these theorems, because once you have reflections, the things change quite dramatically. You can have caustics and things of this type. So you can assume that there are no reflected waves. Wave energy is not conserved. It's wave action that's conserved, which is the mean energy density multiplied by the group velocity. And the reason for that is if the water depth changes, the group velocity will change. And so that's what you need to take into account. If your water depth is constant and changes are induced by something else, then wave energy will be conserved. When you come to look at the global properties, you actually need a different coordinate system. So usually what you do in water wave problems is you choose your mean water level wherever you are to provide your origin. And this gives you a water depth, h, and you work away from there. If you're going to be working in the global system, you need something more like this. And you actually need to have two reference levels. You need to have one at the bottom to show how the depth changes relative to that. And you need to have one at the surface to show you how the free surface changes relative to that. And you don't have to be on a curved reference frame to get changes in the mean water level. This happens quite ordinarily. If you have something like shoaling on a beach, this occurs very, very commonly. Now, I'm not saying that the methods that are being used here would be used for shoaling on a beach. They're not entirely appropriate because you can find better methods for doing it. But there will be a change. If it goes up, it's called the set up. If it goes down, it's called the set down. And you need a datum on the top and you need one on the bottom. So just to distinguish between the two, I've used a capital Z. That may not be entirely clear from where you're looking. A capital Z for this slow frame. Okay? You get changes in the water depth. You get changes in the current. And see what happens. Okay, now the problem with current changes is the way that they can occur. Because you can get upwelling from below, which was mentioned earlier, but you can also get inwelling from the sides in 2 dimensions. So it can change because of two things, inwelling and upwelling. If you have no current, if you have no waves and you just have a current alone, then you can use the Helmholtz vorticity theorem, which you should get from most courses on standard fluid mechanics, and that will give you the changes in the current. You might have to do it numerically, but in principle you can do it because you know about the stream function structure. So you've got these two. there. The waves that most people would know about are Stokes waves. And in Stokes waves, what you do is you write a series of that form up there. And you write a series like that for the local surface elevation. Okay? That's what you do in Stokes waves. It's a power series in epsilon. It's not this. Okay? Because in that one there, you have a harmonic series in that lower one. Because if you look at the series there in M, you've got M equals 1 for the first harmonic, M equals 2, and so on. So the standard Stokes wave that you're used to seeing is a power series in epsilon, but it's not a harmonic series. So you need to bear that in mind when you're going from one to the other. Okay, just some standard points about the structure that you see inside here. If you look at U naught and these types of things that appear in there, then U naught can be a constant current, but you don't have to have a current in the accepted sense because it depends upon the definition of the mass reference frame that you're using. I'm not going into reference frames, but U naught depends upon reference frame. Phi satisfies Laplace's equation, as does each term that you have there. And typically in Stokes, you know that even components only have even harmonics and odd ones have odd harmonics. That comes out of the series solution. And there's a first order series. And if you put U equals 0, you need to be a little bit careful because it pertains to a very particular reference frame. So these things are well known. Okay. What I'm going to take you through to begin with now is the Whitham theory, because I need to move this towards a Whitham representation. This is not the only way of looking at slowly varying methods. You can use averaging methods as well. But I'm going to go to the classical Whitham method and take it from there. Well, the first thing is, Whitham says you look for a series of that form there. If you look at that series there involving the potentials, you see an n in the denominator of one of the terms. That's only there for housekeeping. When you differentiate with respect to, say, z, that n goes, or if you differentiate with respect to x, because theta is just the phase function. Okay, so the first thing is that Stokes waves. No. It's a harmonic series, isn't it? Because just when you look at the terms in the end there, you've got sine n theta. That's just a harmonic series. No mention at this stage of Stokes waves. One other thing is if you look at the structure of that potential, is that the structure that you would ordinarily expect to find for the potential? In this structure, you have two types of terms. You have the local amplitude, local wave number, and the frequency. They're called the primary triad. And you have the slowly varying terms, which in this case is U naught. And you have that gamma term there multiplying T. And you have B, the setup or set down. And the idea is that you want to set up a system that will give you all of these things. So you substitute into the Lagrangian. This Lagrangian has an interesting history. Without the limits that you see there, it was first proposed in 1908 by Hargreaves. And the limits there were proposed by Luke, I think, in 1967. And if you take the variations of that Lagrangian, you will get the equations of motion. And the earlier ones did not get the correct boundary conditions, which is why this one here is quite important. Next step in the Whitham theory, and some people claim that there's a proof of the Whitham theory, other people claim there's just a justification. One of the proofs I've seen is in Russian. I don't read Russian, so I can't tell you whether it's correct or not. You set up an average Lagrangian like that, and you eliminate the local phase behavior. Okay, so just let me go back up to that. If you look there, you've got that phase behavior of sine n theta and cos n theta. you're going to remove that by phase averaging. And you have to be a little bit careful because you've got the boundary conditions in there as well, which are also functions of the phase. So the algebraic effort goes up quite steeply as you go along. Once you have that average Lagrangian, you take the variations with respect to the ANs, capital ANs and lowercase ANs, and they determine everything in terms of the primary triad and the secondary triad. And you can see that once you start going on things like this, it's going to get fairly messy fairly quickly. So often getting to second and third order is as much as you can do. First order will give you the dispersion relation. Here's what the exact terms are when you look at them. The primary one, when you take dl by dA, that gives you the dispersion relation. You take dl by dk, that gives you the wave action equation. And the terms down there, you get the mass flux terms coming up. But there's one important structure that comes out of this. And that's that because you have dl by d little a, the first line of the equations on the right-hand side, dl by dA equals naught, that says that the average Lagrangian for first-order terms must be of that structure there. Sometimes that Lagrangian is described as incomplete, because in theory you can add any constant term inside there, or you can add any constant, or you can add a function of omega and k. But it's enough. If you compare it with the formal definition, this is correct. Okay? It will always give you the dispersion relation. So the dispersion relation I've just written there is g omega k equals 0. And then the question is, how do you determine f? Do you have to go through the whole thing? Well, in theory, yes. In practice, no. Because when you look at that last line, g can only appear in one way. Okay? It can only come in through here. It can't come in through any of the others because there are the expressions for them. So if g only comes in that way, you only have to track that g. And if you track that g, you get the function there that I've labeled f. And now you have a question of faith. Do you believe the Whitham theory or not? Well, whether or not we have a proof for irrotational waves, we want to go to rotational waves. So do you believe it or not? In other words, if you know g, the dispersion relation, for some water wave system and a given current, can you construct that average Lagrangian, which will then give you the required variations? Well, I have to say in this regard, I'm a bit of a missionary because I believe the Whitham theory. Okay. Oops. Yeah, that's right. Oh, that's the wrong way. Up and down are tricky words. Let me show you what some real currents look like. This is taken from a set of experiments in 1994 by Klopman. It's one of the most complete sets of experiments. Okay? And this is where waves follow the current in a wave flume in a laboratory. It's two-dimensional, and it's been measured across the flume to check for two-dimensionality. Would you agree that that's reasonably constant? Okay, would you agree? That's the question that you have. So we have to see whether that works. The reason that you have a lot of points down there is because one of the primary interests of this set of experiments was what happens close to the bed. And the reason that there's a big gap in the middle with that splurge is essentially due to wealth. Normally what you do is you put a laser Doppler or a laser and the Doppler systems on the other side, and you move it up by small amounts. In this case, they had two laser Doppler systems going up. So every one of these is distinct and clear if we blow that up, but they come out as a bit of a splodge from the second laser. So that's the reason for that. So that's waves following the current. If you oppose the current, they look like that. You may be less convinced by the first one, but I'm sure you're convinced that that's more or less a straight line. Don't worry what happens near the bed. You can fit a straight line more or less down there. And one of the very interesting things, and this came up in the previous talk as well, is that if you forget how these things are generated, you can still use an inviscid model to get the kinematics of that and the previous one very accurately. Okay? There are models that will tell you how that works. This phenomenon was first spotted by Ishmael, but Grunewald and Klopman produced a model using the generalized Lagrangian mean method to get these profiles. So I'm sure we're in agreement at this point that we can model that one by a straight line. There are very few studies using the Whitham method in any type of wave environment. This one is from a wave current set. It's a fairly old set. And what this has is, if you look along the bottom, you have a scale of velocities, and the crosses correspond to experimental measurements, and you see predictions in the wave amplitude relative to the still water one, and you get the corresponding wavelength predictions relative to the still water one as well. It's not a bad fit, is it? In this case, as I said, at the top there, the current appeared to be more or less constant. But there's a little bit of a sting in the tail. It depends how your currents are generated. And the case I've just shown you is actually for an opposing current. But because the current was generated by going through a beach and other flow straighteners, instead of being a straight line as you have there, it's almost vertical. But nonetheless, taking the data as it comes, that works very well. Okay, so let's let's go back a little bit. We need to get to rotational currents. This has an important practical application, which we'll come across in a little while. Okay? You cannot use the Whitham theory for a linear profile, because the Whitham theory assumes that you have a velocity potential of a certain structure. There's no velocity potential if you have rotational flow. So consequently, you can't use the Whitham theory. Okay, we can say that now. It's not for debate. But we also know that we have a structure for the average Lagrangian, which we can use. There it is, if you believe the Whitham theory. Okay, so what this says is, if you can get the dispersion relation, we can get the rest, and it should work. There is the Lagrangian for the straight line profile, based upon what you see above. But what you cannot do in this case here is get the higher order terms, because there's no structure for doing it. And instead, what you have to do is use the alternative method, which is a method of averaging. And people have used the method of averaging for these types of things, and they found the setup and the other terms to a good degree of approximation. But you're sort of walking into the unknown here. So we start again. Well, not quite. I'm going to start where we started before, but take a slightly different approach. The Lagrangian that you see on the top there, the Luke Lagrangian, is basically stationary pressure. So, instead of messing around with potentials and things like that, we'll mess around with something else. And thus we'll mess around with the pressure. Okay? And the standard way of dealing with the pressure is, you write it directly as a harmonic series, like that. So the first term that you see there is a hydrostatic term. And then the other terms are the wave-like terms. We have no insistence, a priori, that the magnitude of Pn plus 1 will be less than the magnitude of Pn. Okay, so you don't know that these terms are going to decrease in magnitude. There's no insistence on that. They're just harmonic series. And harmonic series and approximations of this type are used quite widely in the physical world for calculating problems. So, for instance, rather than using Stokes' fifth order theory for many finite amplitudes, you use, say, a Renniken-Fenton method, which is based upon the streamline approximation. It's actually based on a structure like that. If you take that lot there and chuck it into the Lagrangian at the top and average, you get this. Okay, you get this. So in theory, you can start to move along that path. There is a problem. And the problem is, just to point out what it is, this is the zero order term in there. That's a very important quantity. It plays a role similar to the Bernoulli constants. If you look at these here, that term there, then P1 is a term from the first order pressure harmonic. P1 satisfies that system of equations, and it's also linked to the surface amplitude. For students of ODEs, please provide a solution. Not a series solution, just a solution. This is related to the Rayleigh equation. You can solve it numerically, but to make the sort of progress that you would like to make for the case of variations, you would like to get an analytic solution. So you keep hitting these walls all the time. So then the question is the irrotational case a very special case? Yes. But have you done everything in the irrotational case as you should do? Maybe. But these are the questions that you have to answer, even with P1 in the form that you have there. So let's go back to the pressure stream function formulation, which is probably the natural thing to use in a 2D interaction, or even in a 2D flow. So you have the pressure, harmonic expansion. You have the stream functions, harmonic expansion. You put the two together, and you come up with that Helmholtz equation. Okay, so the Helmholtz equation that you have there is well known. Very often you take special cases of that particular equation. You might, for instance, put it into a frame of reference where the wave is stationary, and then the reduction is quite significant. But that's the form that you have. And that forms the basis for a number of numerical methods in this field. So that's the expansion that you have. And basically what you need to do, I'm not going into the boundary conditions for this, but what you need to do is get all the psi's out of this, the individual psi's. So you do it hierarchically, but you have no assumption to begin with that they're different, though it would be nice to argue that the Pn is of order ak to the n and so on. Okay, so now we find that this can't work either, because that's another equation that we can't solve. But that does not mean that what we're doing is incorrect. We can go as far as we can with this. If you do the irrotational wave case in this formulation, you can see what's going to come out. If you just look at the top equation, put u double prime equals naught. So you put u double prime equals naught, drops down to an equation we can all solve. That's what you have for irrotational waves. Okay, and that's the form of the Lagrangian that was on the previous screen, where LP just indicates the pressure with that subscript. Okay, now you write it in terms of the size. That's what it looks like. And in that form, the gamma that you see in there is a constant of integration, a capital gamma, where you determine the P naughts. And that gamma is an important physical quantity. And the reason it's an important physical quantity is it plays a role in numerical methods that use this approach. So in Reneke and Fenton, for example, that gamma is an important quantity. So we would like to know what that is. So there's a bit of algebra involved in that, and that's one of the things that David's going to pick up on Thursday. On that, it's an important problem, and it arises in other contexts. Okay, if you take a constant current, these are the psi's, we know all the solutions. The velocity links, u's and v's, show you the links between the psi's, and if you put all the psi's in terms of phi's, the irrotational part, you get that bit there. You see it LP equals rho gamma h, that line. And if you then compare that with what you have got from the Whitham Lagrangian, then you get that one there labeled LB. And if you look at the difference between the two of them, you can see what happens. Okay? Those should only differ by a constant, and you can show that they do differ by a constant. Okay? You can show that. If you do the same thing for linear current, you're on your way. But the question is this: is that LP that you see there the same as the LB that you see there? Not in terms of the actual terms, but in terms of concept. And of course, there's a little bit of sleight of hand here. Oops. I think the GPS marker to measure my exercise collapsed. So the question is there, are they the same? So where you've been led along the path is the letter gamma for each of them. One, it was just a constant of integration. The other, it has a specific meaning. Should they be the same? No lunch unless you know the answer to that one. Okay, so even at that level, can you use the pressure? But we have an important result coming out of that anyway. If you do the same thing with the linear one again, there's the result. Quite straightforward. If you have an arbitrary current, what can you do? Answer, not a lot. Because you always have to be able to find out something about the string functions. There are approximate methods that you can use. If you assume you have a wave slope, but if you assume that the current is stronger than the wave slope, the non-dimensional current is stronger than the wave slope, you can get that approximate Lagrangian. And that has been used and works pretty well in physical problems. What happens when you have nonlinear waves? Well, if you have nonlinear waves, the world isn't quite the same, of course. For constant current, the Lagrangian takes the structure of what you have up there. Okay? And if you fill in all the bits, that's what it looks like for the wave-like part. That corresponds to Stokes' fifth order. That should be a calligraphic L rather than just an L in that structure. So these are the coefficients at fifth order, and you probably know the story of this, where fifth order was given by Skelby and Hendrickson in 1960, and later when the algebraic checkers came along, somebody found that there was a mistake. It was only at fifth order, but it was corrected. And then an improved checker came along, and that found another mistake, again at fifth order. You always need to be a bit careful with these things. And the story that I usually tell on this one is that you say to students, you should be very careful using proprietary software, because it's usually written by people like you, but they're not as bright as you are. And that shocks them a little bit. And the very first version of Maxima had cosh squared plus sine squared equals 1. So if you know that much, how can you trust the rest of it? Just be a little bit careful. Okay, so that's what you can do for the case of irrotational waves. If you have a linear profile, you can't do any more than we've got there, and the arbitrary profile, we can't do any more than you've got there. Let's take it back a bit. We all know about Bernoulli's theorem, don't we? Yeah, everybody know about Bernoulli's theorem? Do we know about Bernoulli's theorem, or do we think we know about Bernoulli's theorem? Does everybody agree that the first line of mathematics on there for an irrotational flow is Bernoulli's theorem? First integral of the equation of motion. F of t, an arbitrary function. Is this the way we're all taught? Yep. I was taught that way. What you usually do is you get rid of the f of t by redefining phi. Are we agreed on that? So you redefine phi and you get that equation there. And in the context of water waves, what you usually do then is the external body force you write as g, and the pressure you write as P minus PA to get rid of the atmospheric part. And when you do that, that's the equation that you get. And this is the usual, when applied on the free surface, that's the usual dynamic free surface boundary condition that you use to determine all of the quantities. So here's a question for you. Is the time dependency in phi important? Or is the procedure that you're adopting up there correct? This is something that we never really think about, is it? We just do it. But you've already seen a good example of where it is important. Let the Poisson brackets just denote the time average. Okay? And take that Bernoulli form. All I've done there is taken the previous form that you've seen, and on the free surface, I've just taken the time average. Okay, so this is taken from an argument given by Janssen in what he described as the last paper he would ever write. Well, he's written music. I don't know if that counts as paper since he retired. Okay, which of those terms are going to be zero? If you choose an origin in the free surface, would you agree that the mean value of eta must be zero? Okay, so if that's zero, that tells you something about the term on the left-hand side, and it's negative. But up there, you have that term. What can you say about it? Anything else? You can say these things about it. If you look at the various derivatives, they will be zero. And that includes current. Okay? So that says that that term there is constant, and that's usually written as that form there, which isn't quite the same as you have before. And what Janssen did, quoting work for a long time previously by Lundgren, was to use this method here, just by looking at this, applying this on the bed and on the free surface, to show that you get expressions like this, which one man in the audience would know very well because he got them from another method, shoaling on a beach. It's a very elegant way of finding these things, isn't it? Very elegant way, very nice way. Let's see what happens if you just have a current. If you just have a current, but the waves to be zero, if it's a current U naught, are we happy that Bernoulli gives that form there? Yeah. Now integrate it. And you get that form there. Although I didn't say so at the beginning, I was going to say this talk has nothing to do with Klebs potentials. But that is the phi for a Klebs potential. If you use Klebs potentials, which are defined here to be grad phi plus alpha grad beta, which are non-unique and all sorts of things like that, if you replace that u naught by u as a function of z and nothing else, that's the phi bit of it for the correct form. And then you've got alphas and betas. So the question is now, can we do what Janssen did for a rotational flow? Okay, so for this, we only need to start using Bernoulli. This is the form of Bernoulli, or the equivalent to Bernoulli, in Clausius potentials. So instead of just having d phi by dt, you have d phi by dt plus alpha d beta dt from up here.
Well, I was going to ask that a few minutes back when you said...
How far back do you want me to go?
Oh, no, don't go back. I can just rephrase it. You started with him with saying it's the harmonic average of Luke's variational. But you don't have to go back from Luke's variational principle, but you, right, without the current. But you could have started with an update of Luke's variational principle, including the Clausius potentials, and then average over the phase. Is that not an option either?
When you start doing it from the Luke potential, you have at some point to know the structure for the Clausius potentials.
Yes.
So this way, just there it is. If you take the Whitham theory there, that's the phi.
Yes.
Okay, and you're going to substitute then into the equivalent of the bottom down here, where you have alpha d beta dt.
Yes.
Okay.
Which does give you the full equation.
Which gives you the full equation.
Yes.
I agree.
With the current.
With the current.
Yes.
I agree.
But and then the question is, can you not use an equivalent of Whitham starting there?
Can I ask you a question?
What? No.
What do you propose? That's the problem. Some people have heard me talk about Clausius potentials before, and you cannot get solutions in terms of Clausius potentials for an arbitrary u of z.
Sure, but often with the Clausius potentials, after you've done the work and you get the equations for the extra potentials, you can reduce them to normal velocity variables. So that's what I would have in mind.
Okay, I don't think you can do that. But if you can do it, I would be delighted to see it.
No, that's okay. It's a logical question.
It is a logical question. And I didn't say much about Clausius potentials.
No, now you started, I thought I asked, right?
Yeah. Yeah, let's go back to this point here. Yes. I don't see how you can combine them at the end. I know what you're talking about.
Yeah, that surprises me. But it's difficult often.
Yeah. Let's see if we can do the same thing with this as you do in the other one. Okay. First thing is, we know that phi alpha and beta are not unique. Okay? But what you also know is that the combination for nonlinear applications is that d phi dt plus alpha d beta dt is unique. You know, that's what you know. And that's part of the structure giving you the correct equations as pointed out. If we do the same thing as we did on the previous one and take the time average, we don't know what the time dependence is in phi alpha and beta. So we can only really leave it in that form there. But when you take the x and z variations, you get the two lines that are given there, and you get the f, which is above, as given there. And you can show that f then, from here, is given by this. It's u cross omega, where omega is the vorticity, and that's non-zero, because in 2 dimensions, u is in the xz plane and omega is perpendicular to it. And so you hit this problem doing the same thing again. So you cannot, without going through the details here, I said I finished by 1:15. I cannot, in the details going through here, get the result that you want out of that. You hit another brick wall. Something, again, that only works within the Whitham system. Okay, now just let me go back up to the Whitham structure where we were a moment ago. Okay, look at that function of phi. The question that you normally ask is, can I obtain a phi so that u equals grad phi? It's So that, yes, u equals grad phi. We agreed. I'll speak on your behalf and say yes. Why should you have a time dependence in there? That's from working backwards and saying, this will give us what we need for completeness. But it is not the normal way that you approach problems in fluid mechanics. So there's something more in the Bernoulli structure that we need to look at. Most of the time it works very well, but it depends what you want it to do, and you need to look at these things. So this is yet another unresolved problem. Some talks I've given have been titled Unsolved Problems in Water Wave Theories. Well, we solved one of them, so it's Unsolved Problems in Water Wave Theory -1. But since I started looking at this stuff here, now it's back to unsolved problems in water wave theories again, but it's a different problem. Okay, so I'll finish there. Thank you.
Any questions or comments?
Reduce them to silence.
Yeah, ask the question. I asked my question.
Oh, yeah.
I'm off the hook.
Yes, please.
Do you have any ideas how this unsolved problem might be solved?
This one. No, I don't, because it's back to this thing at the end involving the vorticity coming into the Bernoulli constant, so you can't even use the method that Janssen did. I thought you would be able to use that.
So I ask a question again. So,
Please
so
do.
just because when you said, do you know how to determine the Bernoulli constant F, I muttered, no, I have no idea. I mean, I'm just doing something. So have you solved the problem? Because I think where here it's irrotational, here it's irrotational, and you impose the jump, because then you actually get on one side, I think, a non-zero constant. I was just wondering, has anyone solved that? So it's a bit unusual. You impose a hydraulic jump, but to tie them together, I think you need different integration constant.
Well, I think what's often happened there is those problems have always been solved in the linear theory, and the constant you're talking about would be a second order constant. So I don't know. I haven't seen any second order. Robin, do you know any second order?
Because it's kind of the classic
Yeah,
hydraulic
I
problem,
agree.
but you don't
Yes, I
assume
agree.
shallow water
Yes,
flow.
I agree with what you're saying, but I've only seen linear linking, and I have some worries about linking these things. I mean, very often physically they're associated with turbulence, those layers.
Yeah, but you assume that the turbulence happens in basically in a jump, which is an asymptotic
Well,
expression.
you can do, but turbulent bursting is one theory that's been proposed for the Loch Ness Monster, so you have to be a little bit careful on these things.
I think it's a good time to finish.
So,
Adrian? You first, please.
What's the relation between a small gamma and capital gamma? In a general setting, is it the capital gamma?
and
Is
the
a
capital gamma,
function
the
of
capital
time?
gamma is just a constant of integration, and the small gamma is the time dependence, the pseudo phase pressure term, and the pseudo phase that you have in the Whitham expansion. Let's see where it is.
Is there any
It's there.
relation between the two?
Well, no, I just like you to think that there was a relation between the two. But in fact, the pressure does not have the arbitrariness that the form of the potential has. And that's its weakness. So it can't lead you into the mean flow properties. You have to use averaging.
When you take constant vorticity, is there any difference between, I mean, positive, negative, or it's at the same level of? There's no gain to in one case or the other.
Not really, no.
Nothing.
I've seen linear, the constant vorticity up to third order. But again, I'm not sure who's correct. The first paper on that, I think, was 1956 by Tsao. And the next two people to look at it were Ivar Jonsson and his PhD student, Ole Brinkjaer. Ole Brinkjaer got a different version to Tsao. So Jonsson thought that he would try to provide the definitive one, and in turn his was a different version to Brinkjaer's and Tsao's at third order, because the algebra was so difficult. And two other people tried it as well, and they also found. So there was 5 versions of that. But there's no difference, really. Having said that, there can be physical limitations from the slope and the difference between the top and the bottom, because there are certain things that you need to avoid. But otherwise, no, not as far as I've seen.
Then I would like to say the next session begins at 1:30. So we have 68 minutes break for lunch. Thank you very much.